Hello, hello, hello. Okay. Am I audible? Am I audible? Let me check. Let me check. Mic testing 1 2 3. Mic testing 1 2 3. Okay. Hello. Hello. Let me check if I am audible. 1 2 3. 1 2 3. Okay. Hello. Hello. Let me
That's not
check if
bad.
I am audible. 1 2 3. 1 2 3. Hmm. Now, I really want to try the studio voice. High GPU disable effects or close app. High GPU load. I know it's high GPU load. I was the one to do high GPU load. Utilization 100%. Who's using my GPU? Wow. What? Okay, cool. GPU is still 100%. I don't know why. Hmm. But I still want to try it out. Okay, cool. GPU is still 100%. I don't know why. Hmm. But I still want to try it out. Okay, cool. GPU is still 100%. I don't know why. Hmm. But I still want to try it out. Hello, hello, hello. Okay, cool. GPU is still 100%. I don't know why. Hello, hello, hello. Uh, Properties, device.
It's okay.
Hello, hello, hello. Hello, hello, hello. Uh, Properties, device.
It's okay.
Hello, hello, hello.
Hello, how are you?
Hello, hello, hello. Uh, Properties, device.
It's Hello, how are you?
Hello, hello, hello. Properties, device.
Hello, how are you?
Hey yo, what's going on? Hello, hello, hello. Properties, device.
Hello, how are you?
Hey yo, what's going on? Let me change my microphone to real tech. Properties and now studio. Device.
Hello, how are you?
Hey yo, what's going on? Properties and now studio. Device.
Hello, how are you?
This this is testing NVIDIA
Hey
broadcast
yo,
default.
what's going on? Properties and now studio. Device.
Hello, how are you?
I think this is it. This is fine. No worries. Broadcast. I think this is it. This is fine. No worries. Broadcast. I think this is it. This is fine. No worries. Broadcast. I think this is it. This is fine. No worries.
Perfect.
Broadcast. Now let me start. Perfect. Okay. So let's start with LeetCode.io roadmap. I'll also hello. What's going on? What's going on? Playlist. One second.
Hey everyone, in this course we're going to be learning about all the fundamental data structures and algorithms that you need to know, especially with a focus on quicksort is another common sorting algorithm and it's actually very similar to merge sort. The idea is that instead of splitting the array into two equal halves and then sorting those halves, instead, we're going to pick a random value, and for convenience, we usually pick the rightmost value, and this is called the pivot value. So the pivot value is special because what we're going to do is we're going to iterate through every single value in the input array, except for the pivot value, so basically every value before the pivot value. And we're going to compare that value to the pivot. And every value that's less than or equal to the pivot value is going to be in the left partition of the array. So what we're going to do is take the input and partition it into two pieces, a left and right piece, where every value that's less than the pivot, less than or equal to the pivot, is going to go in the left half, and every value that's greater than the pivot is going to go in the right side. And performing this partition is actually pretty simple in terms of code. And we can we're two values over here. We're going to do pointer before we split the array is we take the pivot and swap it with wherever our left pointer would have been. Remember, our left pointer starts here, and since we didn't end up swapping anything here, our left pointer would stay here. So what we're going to do is take 1 and 2 and then swap them, because we know our pivot should go at the beginning. 1 should go at the beginning, 2 should be here. Our
Wait, what
pivot,
just happened?
every value on the right is greater than every value on the left. Now this is where the recursive step comes in. Now let's run quicksort on the left side and run quicksort on the right side. Now before we recursively run quicksort here and here, one thing to notice about the 3 is that it's already in sorted order. Everything to the left of it is less than or equal to it, and everything to the right of it is greater than or equal to it. So this 3 doesn't actually need to be part of our equation anymore. We can just ignore this. So it does exist, but we're not focusing on it. When we run quicksort on this subproblem, let's just focus on these two values. This is already exactly where it needs to be. And that's always going to be true of the pivot value. So now we're going to choose the rightmost element, which is going to be our pivot. So in this case, 1 is our pivot. We're going to start at the beginning of the array. We're going to compare 2 to the pivot value. Is 2 less than or equal to 1? It's not. So we don't do anything. And then we would take our pointer increment to be here. It's at the pivot, so we don't do anything. That's when we stop. And the last thing we do before we split the array is we take the pivot and swap it with wherever our left pointer would have been. Remember, our left pointer starts here, and since we didn't end up swapping anything here, our left pointer would stay here. So what we're going to do is take 1 and 2 and then swap them, because we know our pivot should go at the beginning. 1 should go at the beginning, 2 should be here. And so this is the index that our pivot went to. And I didn't mention this earlier, but when we take the array and then split it into two pieces, we do it based on where the pivot value was inserted. So the pivot value 3 was inserted right into the middle. That's why we took the first 3 values and then put them over here, even though we didn't actually include the last value. And then we took all values to the right of that pivot and then, ran quicksort on them over here. But so now that our pivot was over here, we're going to take the 1 and it will go on the right side, and then all the remaining values, in this case 2, are going to go here, and that's essentially the base case anyway. So when we run quicksort on this and this, we're not going to do anything. Of course, an individual element is already sorted. And remember, for quicksort, we're not allocating any extra memory. These swaps that we're doing are happening in place. That's the advantage of quicksort over a merge sort. We don't actually have to allocate extra arrays. Now, running quicksort on these two elements, this is going to be our pivot. This is where our pointer is going to start, and this is also where our left pointer is going to be the pointer that tells us where to insert the next element that's less than or equal to the pivot. So is 6 less than or equal to the pivot? Nope. So we take our pointer, our left pointer will stay here, but our I pointer will be incremented over here. And that's how you know we can stop when we reach the pivot, and then the pivot will always go to the position that the left pointer stopped at. It was over here, so we swap these two values. So this would be a 4, and then this would be a 6, and then we would run quicksort on these two subproblems, 4 and 6, but this is the base case, this is also the base case, so we're done. Now remember, this is happening in place. These are not extra arrays. So if this is in the first position, this is in the second position, we know that 3 was in the third position, right? And that was always going to stay there. This is in the fourth and this is in the fifth. We have a sorted array. Now, based on this example, the time complexity looks very similar to merge sort because we're breaking it up roughly into equal halves. But the thing about the pivot is we're always picking the rightmost value, and it might not result in equal halves. So if the elements were arranged a bit differently, in this case, they're already in sorted order, we would have 6 be our pivot. And what we would end up doing is partitioning every value less than or equal to 6 on the left side. All of these values are less than or equal to 6. So in that case, we would split this into 2 subproblems where we have the first 4 values over here, 1, 2, 3, 4. And then on the right side, we would just have 6. And then this 4 would be the pivot when we're running this subproblem, which would, keep the values in the same exact order. All these are less than or equal to 4. So then this would end up splitting it into something like this, 1, 2, 3, and then 4 would be over here. And we would essentially continue doing this until we complete it, which would look like this, 1, 2, 3. And then lastly, we would split this into 1 and 2, the individual values. But then this, all of a sudden, the height of this becomes n, where previously, if we split it into equal halves, we know then the height of it is going to be log n. But in this case, we're not splitting it into equal halves. So in the worst case, the height of this is going to be big O of n. Now for each level, we're still having to iterate through approximately the size of the entire input. That's approximately how many we're going to have on each level. So in that case, the overall time complexity becomes n squared in the worst case. So that kind of shows us that quicksort is not necessarily better than merge sort. But on average, this is not going to happen. This is the worst possible case where the input is already sorted. One way to get around this is not to pick the pivot as the rightmost element. It's to take, maybe the leftmost value, the rightmost value, and the middle value, and among those three, choose the middle value and then use that as the pivot. So the way we've been selecting our pivot is a bit naive, but there are optimizations you can do which will help us to make sure that we don't hit this worst possible case. So on average, if we do split the two, if we split the array into 2 roughly equal halves, then the time complexity of this obviously is going to be very similar to merge sort. In fact, the height is going to be log n, and since we know each step we're doing an O of n log to them. If array is less than or equal to 1, then the array is already sorted, we can return. Otherwise, we're going to pick our pivot. In this case, we're doing it the naive way where we're just taking the rightmost element. We're also initializing our left pointer to S, which is the start of the array. And that left pointer is basically what's going to tell us where we should insert the next value that's less than or equal to the pivot. So now to actually run the partition, we have a single pointer I. That's that pointer I've been referring to on the bottom, just scanning through the input. And we check, is this value less than or equal to the pivot? That's what we're checking here. If it is, we're going to perform a swap. If it's not, we don't do anything. In this case, it's not less than or equal to the pivot. We don't do anything. We increment our pointer to be over here. Is this less than or equal to the pivot? Yes, it is. So into a value, swap it with whatever happens to be at the left index. So in this problem, and we're taking left minus 1 because we know at left the perfect logic happens to generally array 7 is not less than 5, 3 is less than 5, so we swap these two values. So now the 3 goes before the 7. We'll look at this value, it's not less than or equal to 5. Now the 3 are pivot, so n sorting editor is to be. So the last question, there is. So now the 3 goes before the 7. At this, 4 is less than or equal to 5, so this is going to get swapped in the next position, which is over here. And you can probably see where I'm going with this. So swap these. So now our 3 is here, our 4 is here, and we have a couple 7s over here. I mean, the partition worked perfectly, but you can see that the original relative
Yep,
order of
true.
the 7s, the red 7 was here and the yellow 7 was over here. But now the yellow 7 goes before the red 7. So this definitely does not preserve the relative order of values when there's a tie between them. So generally speaking, quicksort is not stable. So now it's time for a
Okay. Just to summarize the whole video, quicksort is an
quicksort is an
extension or is similar to the merge sort. So similar in what sense? Similar in a sense that we also uh, differentiate arrays. Okay, differentiate arrays in what? From a pivot. Differentiate arrays from a pivot. Pivot can be taken from anywhere. There are optimized possible solution to choose pivot. That's one of the point. The other point is, let me just take 1, 2, 3, 4. That's 5. Let's say we have 6, 1, 3, 7. No, 4, 5. Okay, very standard. There is there will be 2 pointers. 2 pointers. Left pointer will be at the start. Right pointer at pivot. We basically have to bifurcate what values are greater or lesser than the pivot point. So in that sense, this is greater. Pivot is 4 for us. Pivot. Eh, wait a
another
second.
placed where this pointer happens. The less than or equal to values will be here and the greater values will be here. So let's start doing that. So we're actually going to have 2 pointers. One pointer is just going to help us iterate through here, and then the
Hmm.
second pointer is going to tell us where we should insert the next value that is less than or equal to 3. So
Oh, no, 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 no. There will be 2 pointers. The left pointer is basically for iteration. The other pointer will be uh, to check if the value is less than pivot, right? Now to conclude that, let's use the example of 6, 5, 2, 3, 4. For the first point, 6 is greater than 4. Let's just, the pivot will be something like 6, 5, 2, 3, 4. It will come here. The next one, 2, 3, 4. The next one. Now, 2 is less than 4. Is less than 4. So that means we will shift 6 into. We will replace, we will interchange 6 into. So 2, 5, 6. Point will come here. 3, 4. Pointer will come here. And the pointer will increase from here, right? Mm, 2, 3, 6, 5, 4. The pointer is here. Now the next pointer will come here. Okay. 4, 3 is less than. Oh, that's smart. Okay, it automatically is sorted now. So now, we will bifurcate this from the pivot. So that means 2, 3, 4, 5, 6. Again,
Hello. Hello.
hello, hello, property, hello. No worries. That's fine. That's fine. So now we will choose pivot as 3. 2 is less than 3. We do not require 2. 2, 3. Okay. 2 is less than blah blah. Not required blah blah. Again 6 as pivot. 5 less than 5, 6. Base case. Now we will add 4 and boom. It's here. It's here. Perfect. I understood. Now let's go to the bucket sort. Bucket sorts. I don't know
Now
why
it's
there is
time
something
for
called bucket sort.
another sorting algorithm called bucket sort. Are you surprised at how many sorting algorithms there are? You
Yes, I
should be, because
am.
there's a lot more sorting algorithms that we're not even going to cover. But bucket sort is
It's not
definitely
possible.
worth covering because it's unique in that actually it can run in big O of n time, even in the worst case. So it's super efficient. So why did we even bother learning the other algorithms that run in, let's say, n log n time? Well, that's the downside of bucket sort. It's very rare that you're able to use bucket sort. It's sort of a forbidden technique, which very rarely gets to be used. And that's because there needs to be certain constraints for the problem. In this case, the constraint is on the specific values that we are sorting. We're only allowed to use bucket sort if we're guaranteed that all the values that we're sorting fit within a finite range. So in this case, the only values we have are 0, 1, and 2. So we can say that the range of values is in between 0 and 2. Now, typically when you have an array of integers, usually the integer is bounded, like it might be a 32-bit integer or a 64-bit integer, and therefore we would have a range, right, like -2 to the power of 32 approximately, all the way to 2 to the power of 32 positive approximately. So we could say that that's our range, but that's a really, really big range, and that usually doesn't qualify for bucket sort. We're talking about generally smaller ranges, but in this case, we have a very small range, 0 to 2. I mean, you could have a lot bigger, 0 to 100, or maybe even 1,000, or 10,000, or 100,000, right? Like that's still relatively small. Back to our example. We have this constraint, so we can use bucket sort. So what are we going to do? Well, for every single value in our range, in this case, we have a 0, a 1, and a 2, we're going to create a bucket for every single value. That's where the name bucket sort comes from. So for 0, we're going to have a bucket. For 1, we're going to have a bucket. And for 2, we're going to have a bucket. So I have an array of 3 values. This is where each of our buckets is going to go. So each of our buckets is basically a value itself. So for this array, we have indexes 0, 1, and 2. So conveniently for us in this case, the 0 is going to map to the 0 index, 1 is going to map to the 1 index, and 2 is going to map to the 2. It's not necessarily always going to be the case like this. For example, instead of having a 2 here, we could have had, let's say, a 4. In that case, we would just, arbitrarily put the 4 in this spot. The point is, for each of these values, we have it mapped to a position, and what this position is going to represent is the number of zeros that we have. So what we're going to do here is go through this array, count how many zeros we have, and then put that count over here. So we know we have 2 zeros, so 2 would go over here. Here we're going to put how many 1s are in the input array. We just have a single 1, so we're going to put 1 here. How many 2s are in the array? We have 1, 2, 3, so we're going to put a 3 over here. Now, what would be the time complexity of counting all of these? You might think we have to pass through the input 3 times, 1 for each of our buckets, but we actually don't. Let me just quickly show you how we would actually go about counting these. It's mostly straightforward. We would have an index, right, like I, starting at the beginning of the array. And actually just jumping into the code really quickly, assuming we're given an array like this, which looks exactly as our example, and we have our counts, we're going to have an I pointer going from the beginning of the array all the way to the end. And what we're going to do is take this value to, well, first let's talk about how we're going to initialize our counts. Initially, we're going to say we have 0 zeros, we have 0 1s, and we have 0 2s. But as we iterate, we're going to get to the first value, we have a 2. So what we want to do is increment our number of 2s. We can do that by going to count. Any program in any language would follow. So we have n, and then in the inner loop, we're going to have a second pointer. Let's call it j, which you can see j is not actually being used anywhere, but we're just using this pointer to iterate this many times. So let's forget about j. Let's just see how many times are we iterating. Well, 0 to counts of n. So basically what I'm saying here is we're going to iterate this many times. At this point, our n pointer is here, so we're going to iterate 2 times. Now, what exactly are we going to do? We can see we have a third pointer, I. This is important because I is going to tell us where to fill in the value. Initially, I is going to be at 0. Of course, we would want to fill in starting from the beginning. So we're going to fill this position with whatever n happens to be. We know n is the value, 0 is the value, so we're going to put 0 over here. And how many times are we going to iterate over this loop? Well, whatever counts of n is, 2 times. I hope it's starting to make sense now. We have 2 zeros, so we're going to put 2 zeros at the beginning of our array. So we're going to increment I now to be over here. We're going to put a 0 over here. And then our inner loop is going to finish executing. And then we're going to go back to the outer loop. Now our n is going to be incremented. Our n is going to go over here now. So now
Basically, what he's trying to say is the range has to be in an order. So let's say the range is 0, 1, 3, 1, 0. Then it should be 1, 2, 3, 4. That means um, that means even though so the counts table using like 2, 2, 0, 1. It will be something like this. It will still have the, and then we can iterate over the counts table, get the value, and push the number of zeros there. Perfect, understood. Let's sort colors. Okay, it's a medium problem. It's a medium problem. Let's see what we can do. Given an array nums with n objects colored red, white, blue, sort them in place so that the objects of the same color adjacent with the colors in order red, white, and blue. The color red, white, and blue. We will use integer 0, 1, 2. 0, 1, 2 represents red, white, and blue. You must solve the problem using library sort libraries without using. Yeah, understood. Okay, cool. So what we gonna do is we first of all we're gonna change the okay. Let's say red, correct? Count will be something like I'm not sure how is it. Uh, mm, okay. So now we have for the case of 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 2, 0, 2, 1, 1, 0. So now uh, we have the case of so now we have the values 0, 1, 2. uh, 2, 2, 2. We have the case, right? We just have to iterate over the counts. We just have to iterate over the counts array, read the number of so it's like a nested for loop for in range. For k in so
Now, how many times are we going to
ah so they are using something else. I wonder. Uh, 10 because of 0.
Next, let's look at the binary search algorithm, which is very related to sorting. And that's because binary search can only run on an input that is already in some type of sorted order. Because binary search is sort of an algorithm that you might already know intuitively. If you're searching for something, in the worst case, you would have to look at every single value in the input to find what you're looking for. And let's say you were looking for an 8. In this example, you wouldn't reach that until the last position. So you would have to look through all of these before you realized, well, the 8 was at the end. Now, only if you knew that the input was actually in sorted order, you could have done it more efficiently. And the idea is the same with dictionaries. When we have a really massive list of words, we put them in alphabetical order in a dictionary. So if you're looking for the word banana in the dictionary, let's say you go at the halfway point of the dictionary and we find words starting with the character J. At that point, where would we go? Would we go to the second half of the dictionary or the first half of the dictionary? Well, we know the character B starts before the character J, so then we would go to the first half of the dictionary and then look somewhere over there. The idea is the exact same behind binary search. Another example, if I told you to guess a number between 1 and 100, and I told
Oh, but I have to find the index.
You, if you guess wrong, I'll tell you if your guess was too small or too big. Of course, what you would do is guess 50. So the answer, only do it once, you can repeat this operation. So if I told you your guess is too big and the real answer is between 1 and 49, what would you guess? Would you guess 2? No, you wouldn't guess 2. Because there's two possibilities. I tell you that your guess is too big. That's the good case, because if 2 is too big, then that means the only answer left is 1, so you found the answer. But what if I tell you your guess is too small? Then the answer is somewhere between 3 and 49. You didn't really narrow down much. You only narrowed down like 2 values. So that's why we guessed the halfway point. It's less risky because we know every single time we're going to eliminate at least half of the possibilities. So in this case, we would guess something like 25. And maybe I tell you your guess is again too big, so then we know that the real answer is somewhere between 1 and 24. We narrowed down half of the possibilities again. This is the idea behind binary search. Now, it's most common to run binary search on some input, usually an array. And it's very important for the input to be in sorted order, because if call them the left and right pointer, but sometimes people will call it the low and the high pointer. Basically, it's our two boundaries which make up our search space. So by taking our two boundaries and adding them together and then dividing that by 2, we can get a
याद आ गया मुझे याद आ गया L equals to 0 R equals to len of num minus 1 Z equals to plus R. If
divided by, this is what our right pointer to be the length of the array minus 1. And then we start looping. We calculate our mid pointer between the left and right pointer, dividing by 2. And then we want to check the value at the midpoint in our search. Mid, it's not the target. We would cross all these out. Our target must be somewhere over here. So among these, we approximate the middle. Half, aren't we taking